This is lesson 6 of the Quantum Mechanics A mini lecture series. And I'm going to be talking about Planck's work, part 1. But I'll first start off with what I talked about from a previous video. So suppose you've got intensity and frequency, so a plot of intensity and frequency of blackbody radiation. Suppose you have experimental data which looks like this. And from before, remember Rayleigh-Jean's law worked at low frequencies, failed. Rayleigh-Jean's RJ, failed at high frequencies, and it was dubbed the ultraviolet catastrophe. Wien's law worked at high frequencies, but failed at lower ones. So I'll put that as a W there. But none of the theories, I should say, theoretical classical physicists could fit their theoretical model to the experimental data. And so Max Planck, a German physicist, also known as the father of quantum mechanics, attacked the blackbody problem, and he solved it. At the time, it was believed that the radiation intensity versus frequency plot shouldn't depend on the size or shape of the cavity. And the formula, to explain blackbody radiation should only contain things like temperature, capital T in physics, radiation frequency, so lowercase f, and one or two constants. Constants are numbers. Okay, these are numbers that are designed to make the maths work. Okay, for all cavities and for all colors. So this is what a law, whatever it was, should look like. What it should contain to successfully describe blackbody radiation. Max Planck solved the problem and came up with a formula. Now there's different variations of the formula. I'll just write down this one. It's probably a little simpler to understand, but I'll go through it. E is energy. Remember, physicists were after a description of the energy of a black body and its relation to frequency, F. Frequency is F here, measured in hertz, Hz. T is temperature. F is frequency as well here. E just means exponential. Why is it an exponential? Well, in this case, if you look at the graph, an exponential looks like this. Okay, it's sort of going up, not in a linear way. So this is a linear, straight line graph. When you plot it, exponential looks like this. Okay, so the graph was sort of like an exponential. And C1 and C2 are the constants. Remember the conditions here? The two numbers which would make the theory fit the experiment. And Planck didn't know the physical implications of these constants. Okay, he didn't know what they were. And just to know here that temperature is usually measured in kelvins, degrees Kelvin. Okay, in honor of Lord Kelvin, a physicist, classical physicist. And to go from Kelvin to Celsius to Kelvin, you just add 273.15. And so according to Planck, the cavity was made of a collection of electrical oscillators, okay, that vibrate back and forth. And vibrations give more energy. So the more vibrations, the hotter the cavity. And just like his friend Wien from before, Wilhelm Wien, he wanted to find a formula, and he did. He fit the data successfully. And on 19 October, so a very important date here, a very important date in the history of, possibly the most important date, in my opinion, in the history of in physics, 19 October 1900, Max Planck showed his formula, at the physics seminar of the University of Berlin in Germany. He didn't know what the constants C1 and C2 were. So C1, C sub 1, C sub 2. He didn't know what the implications were, why they were significant, but it just worked. It made the maths and the experimental data work. And his mate, Heinrich Rubin, I can't pronounce it, also a physicist, he was there at the seminar, and he was an experimental physicist, he compared his experimental results with Planck's formula, and he found a perfect match, and he communicated his results to Planck the very next morning. So a very important day in the history of in physics.